In this example, we've got a function f which is a cubic, and we need to find the coordinates of the point of intersection between y equals f of x and its inverse. One way you might think of approaching a problem like this is to take the function f of x, find its inverse, and then set the two equal to each other. Sometimes that will work. However, for some functions, like this one, it can be difficult to find the inverse, and even if you can find the inverse, it can be difficult to solve when you set the function equal to its inverse. So in this video, we're going to look at some different approaches you can take to solving this kind of problem. Let's start by looking at the graph of f and its inverse. In red, we have the function f of x, and in blue we have its inverse. The two graphs meet here, which is also on the line y equals x. That gives us a few different options if we want to try and find the point of intersection. We could try to solve the equation f of x equals its inverse. Another possibility is that we could solve the equation f of x equals x. What we're doing there is finding out where this function equals the line y equals x. The third option is to solve the inverse function equals x. So all three of these equations will solve to give the same answer here. But you may find that one is easier to solve than the others. In this case, we're going to solve f of x equals x. So let's substitute in our function. Since we have an x on both sides, we can cancel. Then we could subtract 27 from both sides and multiply up by the 64. We could pop this into our calculator and cube root, but there's really no need because we can cube root both of these numbers. The cube root of minus 27 is minus 3, cube root of 64 is 4, so I've got minus 3 times 4, which is minus 12. Finding the y value is very simple because they meet on the line y equals x. That means that y is also minus 12. So the coordinates of intersection are minus 12, minus 12. Here's a similar problem for you to try. Pause the video, then come back and check your solution against mine. Welcome back. For this one, we could actually find the inverse of g of x. However, you may find that if you did that, it was still quite difficult to solve g of x equals g to the minus 1 of x. So we're still going to use the same approach as last time. We're going to solve the equation g of x equals x. Substituting in gives us this. We can subtract x from both sides, and we can solve the resulting quadratic in our calculator. That gives us x equals minus 3 plus or minus root 29 over 2. However, if you were to plot g and its inverse on the same set of axes, you'd notice that there was only one intersection point, and that's because we need to make sure that we use the domain that's given. So if our values of x must be bigger than or equal to minus 2, then we won't be able to have the solution where we have minus 3 minus root 29 over 2. Clearly, that is going to be below minus 2. So our coordinates of intersection are minus 3 plus root 29 over 2, minus 3 plus root 29 over 2.